Hey everybody, welcome to the second ever PWLTO Toronto meetup. It's nice to see some people who came to the first one and some new faces. And today we have James MacAulay talking about Elm. And ready to go?
Yeah. All right. So before I get going, I'm just going to do a little quick teaser for why you should actually care about Elm. So before we get into the paper, I'm just going to show you what Elm is in the real world today. So this is the Elm website. Basically, as it says, it's a functional reactive language for interactive applications. It's focused on building GUIs, and right now the implementation is for the web. And it lets you do a whole bunch of really interesting things. So there's a bunch of ways of making GUIs for the web. When you're on the web, of course, as you know, there's a lot of different inputs that you need to deal with. Keyboard, mouse, clicks, voice sometimes. Whatever it is, things are coming in at different times, and you want to make sense of it and be able to reason easily about your programs. So here's a cool little Elm demo. It's a live coding session here. I can move Mario around with the arrow keys and jump him around and stuff. And you'll come to understand the code more by the end of the talk. You can also do to-do lists in Elm. And it's definitely a cliche by now, but actually the reason I bring this up is that the Elm implementation of to-do MVC is probably the most concise that I've ever come across, and has the least baggage. So once you get more comfortable with Elm's syntax and how it works, I really encourage you to check out the code for the to-do MVC example, because it really, I think, is a good example of how it can be very expressive without much extra stuff. One of the things that is nice about Elm is that, as you'll see in the talk, its approach to concurrency and to event-driven programming has a lot of nice properties to do with determinism and being able to really, it kind of funnels all of the events going on into a well-ordered sequence of events, which then always goes through this graph of signals in the same way. So given the same sequence of events coming in, you'll always get the same results. And that gives some really nice properties. And one of the things that this lets you do in a straightforward way, of course, it was a fair amount of work for the people to get this working, but they made a time-traveling debugger. So I can move Mario around. It shows trace. It's a little bit offset there for some reason. But now I can pause it and go into my code. And if I don't like the way he's jumping here, I can, tweak it and go back in time and play it back with that code. And the reason why this is able to work the way it does is because of this, the way that Elm sets up its signal graph is in a very deterministic way. And I think the way that, the fact that things like this are possible also makes programs easier to reason about. Okay, so let's get into the paper. Okay, going to do this now. Okay. So this is the paper, Elm Concurrent FRP for Functional GUIs, written by Evan Czaplicki or Czaplicki, I'm not exactly sure, in 2012. This is Evan. So I'm going to focus on what I find most interesting and what I think are the most important parts of the paper for understanding Elm as a whole. I'm going to kind of gloss over some of the parts that are, I think, either less interesting to me or what I find less important to understanding the whole thing. Another disclaimer is that the Elm described in this thesis paper is not the same Elm as exists in the real world. It's not the same one that's running that Mario demo. Basically, the thesis describes a language which is much more constrained, and it talks about, at the end of the paper, about an implementation for JavaScript, but the paper itself really is talking about a language in the abstract. Please ask questions throughout. If I haven't asked for questions in a while, please just put up your hand. Okay, so let's get into it. Before other stuff, I'm gonna just go through a few notes on syntax. Elm is in the ML family of languages, which means that its syntax works a little bit differently than what you might be used to. It's a strongly typed language. It's got it's type checked. So when we have, the way that types are expressed is with this double colon, or actually in real world Elm, they changed it to single colon, but this just means value v is of the type t. This means a list of values where each value is of type alpha. So alpha there is a type parameter. So this is like, if you're familiar with Java, this is like generics kind of. So we can parameterize our types. We can have types that are like working with other types. This is another way of writing the same thing, a list of alphas, square brackets. This is the same kind of thing, parameterized type, but it's one that is going to come up later on, so I'm just going to point it out. A maybe alpha it's just a container that might contain some instance of the alpha type. So let's say it's a maybe string. It might contain a string, in which case you can unwrap it and get at the string, or it might contain nothing. And it ends up being a nice way of working with like no values, which is safer than nils in other languages. This is how you write function type. So this is a function from some value of type alpha to some value of type beta. And one thing, so that kind of covers most of the stuff you need to know for types. One thing that might trip you up is the function currying. So basically, in ML languages, every function actually only has one argument. Sometimes I might say, well, this function has 3 arguments, but what that actually means in Elm is that once you give it the first argument, it returns a function that takes the next argument. Now, this might seem like it's going to be really annoying, but the language is built for that, so the syntax supports it really nicely. So here is repeat 3 Elm. So you might think of that as taking 2 arguments, repeat the string Elm 3 times, and give me a list of it. Repeat 3 on its own just gives you a function back. And if you assign that to the value thrice, if you call repeat, if you say like thrice equals repeat 3, then you can say thrice Elm, and that's now a function which will repeat something 3 times. So that's how that works. if you're not used to it now, you'll get used to it over the next hour. And sometimes you'll need parentheses, just like in any language, well, most languages. It ends up, it's almost not worth mentioning because it works the same way. Basically, you put parentheses around things that you need to group together so that things aren't ambiguous for the parser. But in these languages, it just happens in different places. So because the argument lists don't have commas between them, then you need the parentheses around arguments if they are composed of, if they are themselves function applications. And then you also can use an operator as a function if you put parentheses around it. And one last thing is you can take regular non-operator functions and use them like infix operators by using backticks. So it's just a way of having things read in a nice way. XOR is like Boolean XOR, so you might want to write it like this. And it also then things also, I think, get operator precedence like other operators. So it can help with readability. OK, background and related works. So functional reactive programming has been around for a while. I think the first paper cited in this one is from around 2000. I forget exactly when. So that discusses classical FRP. So basically, the whole thing with functional reactive programming is that we want to talk about values that change over time, and we want to compose those values together using functional programming. That's the basic idea. So classical FRP talked about behaviors and events as two distinct things. Behaviors it described as a function of some time, like a timestamp, and to some value of some type. So a behavior of strings is, you could think of as like a function from some time to some string. So, or like, let's say mouse position would be like a pair of numbers, like XY coordinates. And so behavior would be like a continuous function. It's like a continuous signal of time to mouse position. And then it had events to talk about discrete events that happen in an instant. So, and the way it talked about events is as a list of pairs of timestamps and some type. So you could have an event like a mouse click, which might just, its type might be represented however you want to represent a mouse click. It would just, you would have some sequence of events would be like a list of tuples like that. Classical FRP has some issues that are detailed in the paper and which Evan goes into in a great talk he gave at Strangeloop this year called Controlling Time and Space, which you should definitely watch. This is one of the things I'm going to gloss over a little bit is kind of the trade-offs of the other systems of FRP. Real-time event-driven FRP modified things a bit. They changed things around to get around some of the issues with classical FRP. So they kind of constrained things to get around some of the space leaks, and I think also I think mostly space leaks, like consuming too much memory from classical FRP. But it ended up with a system where you were more constrained. And I don't have a really good appreciation for in what ways you're more constrained, but the talk, I think the talk you gave at Strangeloop gets into that in a good way. So in this one, they basically recognize that there's this equivalency between an event of some type and a behavior of maybe that type. So the idea there is just that you can model discrete events as a continuous function by saying, well, maybe most of the time there's no event happening, there's no click, there's no mouse click, and then at some discrete point in time, there's that maybe ends up having something in it, like a mouse click. So they call that a signal, and it has the same type signature as classical FRP's behaviors. So then error-wise FRP came along, and it was trying to capture some of the expressiveness of classical FRP that was lost with real-time and event-driven FRP, and they used this thing called arrows, which was based on previous work. You can read all about it elsewhere, but basically, they're kind of like monads, but not quite. Anyway, basically, it was trying to capture the expressiveness of classical FRP, but still get away from the space leaks. So one of the things about these models is there's this, basically event-driven FRP ended up getting away from truly continuous signals, because continuous signals have they aren't really well defined how you deal with really implementing them on computer hardware, because if you with continuous signals, you basically just always want to be computing every signal at every point in time, and so it's kind of wasteful, I think. So they ended up figuring out that you can actually just compute things when you need to, and so you just kind of react to events and then figure out where the mouse is or whatever. Okay, so about signals. I found some of these things a bit confusing at first, so I'm going to go through this a little bit. Okay, a signal is a time-varying value. Okay, so just remember that. So how is this different from any old mutable variable? Okay, if we have a variable a, we assign it the value 1, and we assign it the value 2, it's changing over time. Wow, isn't that what's the point of signals? Okay, the difference is that a signal is actually a value. It represents change over time, but the signal itself, when you work with it in code, it's immutable. When you transform it into other signals through these functions that you're going to see, its behavior doesn't change for anyone else who wants to transform it into different things. So this is nice for all the reasons that immutability is usually nice. It lets you reason about the code better. You can share these signals with other parts of your code and not worry about what other parts of your code are going to do with it. Yeah?
I had a concept of modifiable from only one place.
Modifiable from only one place. Yeah, so I would say that when you create a signal, that's the one time when you can, when you create it, then it's defined, nothing else can change it after that. Yeah. Is that clear? Yeah. Is there any other questions, by the way, at this point? You good? Okay. Okay, so this is another important thing that I was kind of confused about at first. Signals have the notion of being updated periodically. So events come in, like I was talking about before. And sometimes these events don't actually change the current value of the signal. So if you move the mouse around and you have the mouse position signal, it's going to be changing all the time. Whenever events come in for the mouse position, it's going to be probably a new value. But with a click event, at least the way that's represented in Elm, it's called, the value that the signal has is just called unit. So that's the empty parentheses there. It's basically think of it like an empty list or an empty tuple, or it's like nil basically. So that signal always has that value. That's always the current value of the signal. So if you transform it in different ways, like it's just always going to have that value. But when it gets updated, you can respond to that update. So the fact that it's getting updated has meaning. Similarly, so with this FPS function for time, that ends up giving you like a delta of milliseconds, the difference from this timestamp to the last time the signal updated. So you know, if you give like FPS 25, then it gets updated 25 times a second, and every time the value is like 40 some milliseconds, because that's how many, like 25 times 40 is 1,000 or whatever. So that's gonna, you know, often be the same value more than once in a row. Sometimes it'll be different, but either way, it's like it's discrete events that you react to. Okay. Yeah.
So you said that signals are immutable. It's an immutable value. Oh, thank you. A signal is an immutable value, but then you said that signals get updated.
Yeah. Okay. Right. So thanks for asking. Okay. So you'll see how it works, but basically the idea is that you have like this signal called mouse clicks, which the value that as you're working with it in code is an immutable value. You can't do it, there's no way to do anything to mouse clicks to make it behave any differently. And there's no way to, in code, like look at the mouse click signal and like imperatively sample it at some point in time to find out what its current value is. You'll see as we go on, there are only certain ways that you can, like, you can't ever ask for the current value of a signal. You can only ever transform it into other signals based on particular rules. Yeah.
A signal has a value and also a frequency that it updates with, basically. It might update 0 times, it might update 1 time, or it might update like regular or not regular.
Yeah.
So it means kind of 2 values, which makes sense because you have time and value.
Yeah. Yeah, so the type signature for a signal is like, you can have a signal of integers, you can have a signal of strings, a signal of tuples of integers. So that type that the signal is representing, you end up writing functions which get called with like a new value of that type. And I don't have a good word for like that value, basically I'll say the current value when I mean that, you know, the string or the integer, and then I'll say like the signal if I mean mouse clicks. Yeah. Yeah.
So is the idea of what you're saying here that you've got this signal, it's going to constantly be, you know, for some definition of update, it's constantly kind of updating over time. You can't go and say, okay, well, what's the value right now? But what you can do is, as that signal updates, you might do something to it, which then propagates all the way through, and you might do something with whatever that value as it propagates based on the reaction. You can't just at will go, give me the value right now.
Yeah, yeah. And in Elm, you don't really ever have a chance even to, because all of the code you write is just kind of, it's like purely declarative. You're just defining the structure, and then once it gets fired up at runtime, events flow through it, and it's all like, then your code, there are ways of you know, doing all the things that you want to do to put events back in the, you know, you'll see that later on, but yeah, it's like you just define things up front and then it's static. That's a good thing to say, actually. Elm has static signal graphs. Yeah.
Should I wait for the mic? Okay. Do the signals have an established frequency, like a default of some kind? So
No.
do you decide that?
No. So, well, okay, so for time FPS, you do. Part of the definition is you give it a number, and then you get back a signal of these timestamp deltas.
And that's like one kind of signal.
Yeah.
And then
so
you would match it up with another one.
Yeah.
Okay.
So mouse clicks, for example, that gets an event whenever the mouse gets clicked. So every signal is different, basically. Yeah.
Very simple, but what does the ML language stand for?
What does ML stand for?
Meta language.
What is it?
Meta language.
Meta language, right? Yeah. Thank you, Leo. Yeah. So basically the most famous. Haskell is in the ML family. So, and Elm is written. The Elm compiler is.
Disagree with you.
What's that? Okay.
Ron Harper would disagree with you.
Okay. I'm being okay. Controversial already. All right. So, anything else? Okay. Okay. So let's get into the core language. Here is the simplest signal transformation function in Elm. It's called lift, and you can think of it like this. The lift function lifts some other function into the realm of signals. So cos gives you the cosine of some number, and time dot every 0.2 that gives you an event every. It gives you actually the current timestamp every 200 milliseconds. Actually, in real world Elm now, they changed that to be based on milliseconds, so you'd say 200 there. Anyway, so coswave then, I should have written the type declarations here, my bad. But coswave now is a signal of numbers returned by cosine, and it's like the cosine of the timestamp. Fit up to is a function which takes some number w, and this is a little bit trickier, but min is a function which will take 2 arguments, but because of currying, min w is going to give you a function back which will return you the minimum of w and whatever you give it. So lift min w window width will give you the minimum of either w or window width. So, and that's a signal. So you say like fit up to 500, and then you get a signal of numbers that are at least 500, and if it's not 500, then it's the width of the window. Yeah?
So just to be clear, fit up to is a function of a number that return. Can you say out the type signature?
Yeah. Fit up to has the type of, it's a function of a number to a signal of numbers.
And
coswave is just itself a signal of numbers. Yeah.
And just to clarify, you used the phrase fit up to is least, but fit up to is not at least, fit up to is at most.
Yeah, it was in the paper. It may have been poorly named. I'm not sure. Yeah. Are we good? Yeah.
Lift is a type.
Lift is a function. Sorry. So this means.
I'm reading the first line.
Yeah, the first line.
So we're declaring a type lift. Or
We're declaring the type of the function lift. So lift is a function, and to the right of the colons is its type. So I should have gone over this first. So the type of the lift function is it takes a function from some instance of type A to an instance of, and it returns type B. Okay, so that's some function of A to B, and it returns to you a signal, a function. I'm sorry, I screwed up. Yes, thank you. It takes 2 things. It takes a function of A to B and a signal of A's, and it gives you back a signal of B's. So it's like, okay, they are currently discussing this, I believe, on the Elm mailing list about renaming lift to map, or some variation of map. Okay. And that probably makes it simpler.
cos in this case is just a function argument.
A cos is just a regular cosine function. Takes a number, gives it back a number.
Okay, so cos is like a library function here.
Yeah.
Okay.
Yeah.
And then what you're doing with lift is making it take in signals.
Okay. All right, I'm going to keep nodding.
Okay. It'll probably become clear. Okay. Okay. What if we want to combine? What if we want to combine signals?
Thanks, James.
Okay, so lift 2. It takes a function which takes an a and a b and gives you a c. So it takes two things and gives you something else. And it takes a signal of a's, and it takes a signal of b's, and it returns a signal of c's. So this comma here is, that's a way of referring to the function which takes two items and gives you a pair of them back, okay? Yeah, so so lift 2 with, let's call that the pair function, and you give it the cos wave signal from before and some other sine wave signal, and then we get a point which is then a signal of, and all of the values of that signal are pairs of numbers.
So the pair is that a cosine and sine, or something else?
Sorry?
The pair.
The pair?
I mean, this is defining a pair of cosine and sine?
Yeah.
Okay.
Yeah. So lift 2 with the pair ends up combining both of these signals with the pair function. So it's like every time either of these signals updates, that's important. Anytime either of these signals updates, the pair function will get called with both of the signal's current values. Yeah?
That particular one you defined is nice for explanatory value because that point is moving in a counterclockwise circle at all times.
Oh,
It's cos wave, sine wave.
that's fantastic.
There you go.
I didn't realize that. It's moving in a counterclockwise fashion for the video. Okay. Okay, so lift 3. Okay, I'm going to stop after this one, but yeah.
So,
Yes, it's coming. It's coming.
okay, so these are these part of the language, or are we just defining lift 3? Is it something that's part of the language, or?
It is actually part of the language, and it's because of the currying thing. Every function has to take one argument, so they kind of have to do this. I have an appendix to the talk, which hopefully we'll have time for, and I'll talk about a nice trick that they have to not have to be using all these lift functions all the time. They added some syntax to make it nice. So don't worry if you don't understand this one, but we're following the same pattern from before. But what's interesting is that we can define it in terms of lift 2. So because lift 2 already combines functions, this ends up doing it recursively. And basically the thing you need to know is that dollar is function application. So the dollar function takes a function and a value, and it applies the value to the function. So it took me a minute to understand this, but basically we call lift 2 with function application, and the first signal that we give it is a lift 2 of the function with the first two signals, and that ends up being a signal of functions, which you then plug into the function application with the values from S3, and then you get your signal back. Got it? What's that?
The signal of D, right?
Yes, the signal of D's, yes. So whatever the type the S3 function returns, or no, the F function, whatever type that returns, yeah. Good, okay. Okay, so this is then lift n. So we have getting some diagrams just to visualize it. We take in one or more signals, and we combine them somehow in a new signal. Okay, how do we remember the past? Up until now, we've been only transforming values, so we can't remember anything. We're just like, oh yeah, cosine, but what was the last timestamp? I don't know. So fold P lets us do that. And you can think about fold P as, if you're familiar with other fold functions, fold L, fold R, it's also very closely related to reduce or inject, depending on your language. Oh, there should be a space there. Anyway, so basically this is folding not to the left or the right, but into the past or from the past, depending on how you think of it. So this has a signature that's similar to fold or reduce. It takes a function, takes an A and a B, and returns a B. So think of B as the accumulator, okay? And it takes an initial value of B, and it takes a signal of A's, and then it returns a signal of B's. So here's a way of writing anonymous functions, which I didn't mention before, but that's how you do it, at least in the paper. So here we have a function that takes some value k and a word and returns the word with k appended to it. K is a character, actually. So, and a string is like a list of characters. So, and then we start. The base case is empty string. And then the signal of the A type is keys.lastPressed. So that ends up being a signal of characters. And so every time a new character comes in from the keyboard, then it runs through this function, which gets in the character and whatever the accumulator value is, and returns the new accumulator value. So this is going to then be a signal where each new value is a new string with the last character appended. Here's a way of doing a counter. So mouse clicks, start at 0, just increment by 1. The click variable is not used because we're just counting. Is that good? Yeah? Okay. There's the diagram. That's a boring one, but imagine state in here. State. Okay. Okay. Async. So this is one of the important things in the paper. How to deal with asynchronous stuff. We'll get more into the implementation later. But right now, you can think of it like, if you have some slow thing to do, imagine a blocking operation, and you want to make it asynchronous. And basically, that's going to mean that the rest of the signal graph isn't going to wait for it. So we say, this is too slow. Let's just make it asynchronous so that we don't have to wait for it. And basically, that's going to end up, it's like a trade-off that you choose to make. And so then you end up having this part of the signal graph that is like asynchronous with the rest of the graph. And that'll probably become more clear as we go along. But yeah, it's a trade-off that you decide to do in some cases. Okay, part of the language is also lets. So, and it turns out in the paper, the let construct ends up being really important for reasons I'll get into. But you can say, let y equals mouse y, and then you can use it in a couple different places. And if you're familiar with let, that's in other languages, that's it works pretty much the same way. If you're familiar with imperative languages, it's like closest thing to local variable assignment. So yeah. So this is how let is shown in the paper, and the reason they show it this way is because let lets you use a signal in multiple other signals, and the importance of that I'll get into. So here's the expression syntax for Elm. And as you can see, it's pretty small. So this is, again, the thesis paper version of Elm. It's not the one that was running the Mario demo. But so it's pretty constrained, but it has a bunch of, you can do a lot of stuff with this. Yeah. So I mean, one thing is that the basic values are just numbers in here. You can only work with numbers, I think, and yeah. But anyway, it's pretty simple.
So you've shown us the entire language.
Yeah, the entire syntax is there. Yeah.
So like are operators like plus plus defined in terms of let, lift, full P, and anything? Well, operators would be functions.
Operators are functions. So it ends up, so there's some transformations syntax transformations that I'll show later. So I'm not sure actually if like infix, yeah, so that stuff isn't in here, I guess. So I think like for the purposes of like getting the idea across in the paper, it's kind of like a constrained version, yeah. These are the types involved. So this is, don't worry too much about this, but basically we have, this is tau, is that right? Tau? Yeah. And sigma and eta. So tau stands for, I think he said just type. So that's regular types. Sigma stands for signal types. And that includes like functions that involve signals as well. And then eta, I like how he says in the paper that eta with a strong accent can be read as either. Eta, either, I don't know. So, and then that's either one. And basically the reason this is important is because Elm only lets you work with signals in particular ways. You can't, basically, I'll say it, this is the first time I say it, you can't have signals of signals in Elm. Okay, don't worry too much about this. We're running short on time, so I won't get into it either. Yeah, this is, yeah, these are the types. One thing I will say is, if you're interested in like reading this and want to know how to read it, I found the Wikipedia article on the simply typed lambda calculus particularly useful for that. Here are the initialization semantics. Basically, all that I'll say about this is that there are some particular rules in here for transforming like function application into let expressions, and for like transforming let expressions with signals in them into other things. So it kind of has to do with how they need to treat signals differently. And basically it comes down to how they don't want to actually like copy, they don't want to have two different instances of the same signal, because then they're doing like more work than they have to and might cause other semantic issues. That's the gist of it anyway. Okay. Yep. Yep. So my understanding is that what's above is like the given, like the constraint. Yeah. So yeah, it's I read more about it here. So here it's like, so the way to read this is like actually it's like this guy gamma is like a context, a type context, and so you say like E1 is of the type eta when it's in this type context, and then like given all this stuff, then this stuff. Yeah.
Is there like a math notation FAQ somewhere?
So that Wikipedia article I mentioned is the best thing I came across. Yeah, simply typed lambda calculus.
And theorists decide to come up with their own new notation for no reason at all. There you go.
Okay, so this is now getting into the meat of the paper. Why is Elm's FRP, why do we care about it? There's been other FRPs in the past. Well, Elm does concurrency. So let's talk about a couple different things. Synchrony, having different signals be synchronized. What do I mean by that? I mean that you can preserve event order and that you can have determinism. Yes?
Just say, going really back to the start, what forces the introduction of signals? What's the motivation to?
Right, okay.
You explained them, but you didn't
Yeah.
say why
Okay.
they were forces.
So basically, in a purely functional programming language, there's a lot of different reasons why signals might be nice, but the main motivation that he gives in the paper is that in a purely functional programming language, you get all sorts of nice things, like it's easy to reason about your code, and you don't have to worry about things mutating out from under you. But in the real world, values change over time. So how are you going to model that? And in Haskell, you model it with monads in various ways, like the I/O monad. But Elm, so that's basically like signals are Elm's answer, and so they let you model changing state. Yeah. So it's like changing state while still being able to write pure functions. Yeah. So why? Okay, I'm still talking about synchrony again. So let's say you have your program and it's dealing with an API and it's gonna get these messages back. And the first message you get, let's say you have like a WebSocket and you're getting new messages. So here you get this message from me and it says I'm having fun. And you have a signal graph, or let's say you're using some like JavaScript MVC framework that most of them have solved this problem, but I think some of them haven't. Where anyway, like let's say you have messages coming in, and you have some like computed property that's based on the new message coming in. And then another message comes in, and sorry for the indentation, and it's from someone else, and let's say your computed properties, you have one computed property for the author and another one for the content, and you're going to show them on the screen. And you get this message in, and then you get this message in, and one of those computed properties is going to update before the other one. So people are going to think that I don't like parsnips, and I do like parsnips. That's basically the problem. So basically synchronizing these things so that the end result ends up being, when you combine these things together, the end result ends up being synchronous and consistent across, basically for each update, you want a consistent view of the world according to that new update, Okay, so let's get into some graphs. Okay, in Elm, you have the big scary world of events, and they are in all sorts of weird orders, and it's hard to reason about anything. And then they come in and to what's something called the global event dispatcher. And that basically is a big funnel, and it spits out nicely ordered events on the other side. It actually broadcasts those events to all of the different inputs. So let's say you have mouse position and mouse clicks. All of them get all of the events, and you'll see why in a minute. But then the events propagate through the graph of signals. So here's some different signals. Here's an input signal, mouse.x, so the x coordinate, just the x coordinate. Lift to min, so like the minimum of two other signals. This one is the square root of the x coordinate of the mouse. This one is a light expression with which lets you add a signal to itself. Okay, and yeah, okay. So then here's a simple graph, and this is just an example to show why asynchronous stuff is important too. So here we have a words input coming in from somewhere, maybe a text field box, and there's going to be some signal which translates those words into French, and then we're going to pair them together again. So we're going to say, dog and chien, and then we're going to pair that with the mouse for some reason. Well, yeah, right. A common UI problem, indeed. Basically, the issue here is that translating a word into French is going to take longer than your next mouse event. So you don't want that to hold up the whole graph. So we want asynchrony. Okay. Yep. Yep.
I'm confused. Like, you don't know, we discussed it earlier, but like, you don't know when a signal is going to be the next value. So how do you know you should wait?
When you write the program, you have to know when you write the program which signals are going to be slow and which aren't, basically. So
my point is like, what does slow means? Like,
it means anything that it's like when you're building UIs in some other multi-threaded environment and you don't want to put something on the same thread as the UI.
Something that does a network operation.
I understand what slow means in the real world, but the problem is like, you don't know when the user is going to click the mouse the next time, right? So you just said we don't want the signal graph to wait.
Right.
For the translation to French to be complete. But I don't understand how the signal graph can wait if you never know for any given signal when the next value is going to come out of it.
Okay, so
I just don't understand the idea of like the signal graph waiting.
okay, so this would be I think I'm probably explaining things in a little bit the wrong order. So basically, what happens when actually I'm gonna use this. All right. So let's say this is clicks, and this is position, and I don't know. Let's just pair them together. So okay. So let's say that's our signal graph. Here's the global event dispatch, and it's going to be sending events to, it's going to be broadcasting them to all the inputs, like I was saying before. And so the way this ends up happening behind the scenes is that these events are like, let's say the first thing that happens is that the mouse moves. So you get a position event, and that's going to be like position 10, 10. So let's say that's the first thing that happens. So that event gets sent to the position input, but it also gets sent to the clicks input. And the reason why it's sent to the clicks input is so that the clicks input knows that something happened. So what happens from there, both of them get the position. The position input is going to send a change message of 1010. And clicks is going to send a no change message. And the value of the click signal is always this empty thing. So then this lift signal ends up being the combination of them. So the reason why this no change is here is so that it's to maintain consistency. So it's like what I was talking before about the two different messages, and you don't want to get the like let's say with the messages example, let's say we have two lift nodes. One of them is name, like author, and one of them is content. So if there's some combination, like name, content, and then we pair them together. So if some event up here ends up getting if it ends up updating both of them at the same time, so that here I'm saying, sorry about this, so that both of these things would get change events as part of the same, from the same event coming. So the name is changing and the content is changing. Then that's great. Then we can know to pair them together because we got a new message from the API, and then we get a name from it and we get a content from it. If we don't have the no change messages and we only have change messages, then what's going to happen here is that the value of this one is going to be, James, with yay, and then once the new message comes in, well, this one happens to update first behind the scenes, and then if we only had change messages, then this one would just have to say okay, well, I got a new content, so now James is saying boo, right?
So, if I can,
yeah.
Back to the original question. Because every time you get an event,
yeah.
the whole graph is updated. You can't have basically something slow in the middle of the process.
Exactly. Right.
That's because everything is updated
because
every time you have an
yeah.
event.
So whenever any event comes in, these, maybe only one kind of little line of the tree ends up getting change events, and then the rest of them, they get no change events, and they propagate also. And every signal always waits for all of its parents to either give it a change or a no change. And so that's why you want to separate out these slow things. Yeah.
I have a comment to go with that. So an important thing here is this all is FRP, I think in general, is predicated on the idea that you have a single global event loop that's feeding into everything. It's inherently in many ways sort of single threaded like that. You don't have multiple completely independent threads sending in inputs. And that allows you to do this stuff as it is forcing and this is why
Yeah.
a lot of people love this GUIs, I think, as a primary motivator, because it really is modeling that kind of similar situation.
Yeah, so it's behind the scenes, you can have asynchronous stuff, and you can have these events coming in from the outside. The outside world is asynchronous, but then overlaid on that, you have this kind of synchronous world, which can be nice. Yeah. All right. So So yeah, this is just, okay, so then basically if we've decided that word pairs is, yeah, so we have, so this one is called word pairs. It's pairing words with the French words. And then we have the mouse. So if we decided that that's slow, we want to separate it out, then we use the async function. So we say, let pairs equals async word pairs in lift to, so pairing together the word pairs with the mouse position. So this, because the signal that this let expression evaluates to is, it has two parents then. It has the async word pairs, and it has mouse position. And this is what it looks like. So this graph is still slow. Words is an input. You could, like, you can imagine an arrow being drawn also from this same global event dispatcher to words, okay? This ends up being slow, but it's okay because we're only displaying stuff based on this one, and it's separated from it. So what happens is that every time this comes with an output, which is going to be slow, we go back into the world of asynchrony where we lose the determinism guarantees, but we don't actually care about them in this case because we don't need to, like, the mouse position doesn't have anything to do with French, So then whenever this is done, whenever it happens to finish, then it goes back to the dispatcher, which then broadcasts an event to all of the inputs again. The change and no change events, I should say actually, so just the no change events are discarded here at the bottom here. So every time there's a change event here, then it goes to the dispatcher, which then feeds back into pairs. But pairs is also getting all of the events from mouse as well. So then you get like a bunch of no changes over here and a bunch of changes on mouse. Is that, yeah?
When the words subgraph triggers a change event that goes into the GED, does that then get rebroadcast back into the words input?
Yes, it does. And it ends up being a no change event that, so words would end up getting, it would end up getting an event of a topic, like the topic of the event would be, would identify like this signal somehow. And it would just say, like, because this signal is not, like this guy doesn't actually care about this. This guy only cares about the text field or whatever it is. So it's going to be, that's going to mean no changes.
And while that word subgraph is busy processing, it's still getting events that it does care about, right, as you continue typing.
So what this requires is that the, is that, oh, okay. What this requires is that you can't have words updating faster than it takes to translate words to French. So if you did it on every key press, then that might take too long.
Does it like queue them up?
Yeah, it would queue them up.
Right. So
Yeah.
you would be getting French translations for maybe a couple of minutes even if you type really fast.
Yeah, right. And I think basically you would, if you want to do it on every key press, then you want to probably do debouncing or whatever, and you would wire up the signals somehow to do that. Yeah.
But you have to do that manually.
Yeah.
Otherwise, words is getting every single input, and even if it's getting done in the background, and it's way out of date with the rest of the graph, it's
Yeah.
still chugging through them one by one.
Mm-hmm. Yeah. Yep.
So the pair in the bottom right corner, that's is that only changing when both pairs and mouse changed, or is it going
No.
to change when one of them does?
One of them.
Okay.
So, yeah, it's with a lift signal. When a lift signal has any of its inputs, any of its parent signals as a change event, then that's going to change the child.
Right. So, because you were giving an example on the whiteboard.
Yeah.
Like, I guess person and message, and it was like James saying yay, and then the message changed to not the person, and then you had the pair like James saying no.
So that wouldn't happen in Elm. That's what I was illustrating. I was illustrating that as the problem that Elm avoids.
Right, but right now if
Yeah.
I'm changing, if the pair is changing on either, if the pair is changing, if like either of the two things going into it have a change signal, how wouldn't I have the same thing happen if I have like a signal?
Okay, right. I understand.
Right?
So the reason why, so what would happen in Elm if you have a new message coming in with an author and content is that the single event of that message arriving is going to be associated with one incoming event, one input signal, and then you would have like lift nodes that one of them would get the author, one of them would get the content. And the crucial thing is that both of them would be change events, and you would get both the new author and the new content at the same time. There would never, and one of the things is that all the nodes, they wait for all of their parents.
Right.
So you wait for you might get the content first, but in Elm the signal will wait to find out if whatever, because let's say the author, well, in this case, let's say mouse is changed and pairs is not changed. If it gets pairs first, no change, it's going to wait to see if mouse has changed, and vice versa. Yeah. Okay, so I'm really glad. Was it Mattia that you asked that and spawned that conversation? Because that was exactly what needed to happen. So here is a little demo, which I need to mirror my display. Okay, so here we have. Can you see that all right? So here we see, I've gone to a lot of trouble here to recreate the internal semantics of these change messages and no change messages. So it turns out that in Elm, while behind the scenes there are these semantics of messages being passed around, the language doesn't expose it directly. There's no function that lets you give in a signal and get out a signal of the messages that are going on behind the scenes. So I figured out some convoluted way that I won't get into to kind of reconstruct it. But you can see, basically, this is the signal that's being demoed. This syntax, it's just a way of slotting in mouse position as the last argument, and I just did it this way so that it's more readable. So we are taking the mouse position, but we're only sampling it every time there's a mouse click. That's the way to read that. So this top thing here, this pair of numbers, is the output. That is the value of click positions. And so every time I click, it updates to wherever my mouse is. And then below it, you can see the two inputs and the output, and which message is currently being, the last message to flow through that part of the signal graph. So, so my mouse position, you can see, is changing all the time. And then every time I click, it's the clicks and the click positions that changes. So the output only changes when you get a click, and when I click, the mouse position is a no change, because that's not the event that came in that time was just a click, was not a mouse position. Is that clear? Okay. Okay. So, by the way, this is turning out to be kind of long. How is everyone doing? Good? Okay. Okay, what do I, oh yeah. Okay, so let's get into some concurrent ML. So this is the language that Evan decided to do the main implementation of Elm in the paper. And it's kind of atypical of programming language papers in that he didn't just write a bunch of math to talk about the language. It's really great. He actually used another programming language to talk about the language, which made it readable for me. Or it wasn't actually readable for me at first because I didn't know ML, but after staring at it long enough, I kind of figured it out. So, so some things to know about concurrent ML. Basically, it's ML of so the syntax looks the same as what you've been seeing, but it's got this concurrency mechanism that is actually remarkably similar to what you might be familiar with in Go or with closures core async. Basically, you have mailboxes, which are like channels in those other languages. So you can, these are, in concurrent ML, they are actually unbounded buffered queues. You can put things on them with send, you can take things off of them with receive, and if you try to receive and there's nothing on in the mailbox yet, then you wait for it. And if you try to send and there's nobody to take it, then actually it's buffered. So you can always put something on it and not wait. Yeah, I think, yeah. So, and then M-channel is like a mailbox, but it's like a multicast. So you have like one sender, but multiple receivers. And the way that the receiving works is you call the port function on the M-channel, and then you get something back that's like a mailbox, but you can only receive from it, I think. And then there's another function called spawn, which takes a function and spawns it off in another process-like thing. Okay, here's some syntax. So basically, I'm not actually sure what's with these square bracket things, but somehow they mean, basically when you see these square brackets around an expression, then replace it mentally with, or like if you want to, replace it mentally with a pair of, and like the first thing in the pair is going to be the initial value of a signal, and the second thing in the pair is going to be a port, like we just saw that function port. So it's going to be like something that you can receive from. Here's some helper functions I won't get into. I'm going to kind of go quickly through this stuff. Basically, you can see here there's the event dispatch and a display loop. Excuse me. So we end up like spawning a couple functions for this, and there ends up being like a mailbox for new events, and yeah. So over the next few slides, I'm gonna basically go through like the implementations of these different things, and yeah. So here's an input node. Events come from the dispatch, and they get spit out as messages into the graph. Here's the code for it. Again, I'm going to gloss over it, but basically, this syntax here means like an input signal. Don't worry about it too much. And then we say that's going to, like, this is going to be the return value of it, an initial value, and this channel cout. But before we get that return value, we're going to spawn this loop function. And we get the loop function and v and cout from this where clause. So this is like an inverted let. Basically, this is where we have all the definitions, and then we return this thing up above. So, so when you define an input, you give it an ID. So that's like some unique ID that only mouse position has or something. A channel of inputs and an initial value. And so then you say, get a port from this multicast and make a mailbox as our output channel, and get a channel of event IDs that come in from the global event dispatch. And then we loop, and then we say, if, this is the part that says, like, if this is my kind of event, if the event if I'm mouse position and the event I'm getting is for a mouse position, then I'm going to send a change message. Otherwise, I'm going to send a no change message with the previous value of the loop. So we run the loop, and then we send it out, and then we loop back with whatever the contents of the message is. So the value of like body of message ends up being the actual mouse position. Lift signals. Same kind of thing going on. We spawn a loop and we return this signal pair. So here we have like potentially a bunch of signals, and we make a bunch of pairs out of it, and we are going to we make an output, and our first value is going to be this function that we've got applied to all of the initial values. So the initial value is like what you'd expect from a lift node. Then we do the loop, and we wait for all of the signals, and then we assign them to some local bindings. And this means, like, if any of them are change events, then send out a change event with the function applied to all the values. Otherwise, send out a no change event with the previous value. Got it? OK. Fold P. So here we've got same kind of preamble. So here's the input signal. We get the pair from that, but this time we only care about the input channel because we're getting our initial value from the base that was provided. So then we loop, and the accumulator is going to, basically we're changing the accumulator every time. We are going to then receive from the input channel, and if it's a no change, we send out a no change with the previous accumulator. If it's a change, then and it of some value, then we send out a new change with the like folding function applied to the new value and the accumulator. and then we loop. Good? Let expressions. Here is some trickery to basically take any signal that you bind in the let expression. It's going to take the output channel. So this is the way that this little Elm ends up taking the output channels. So the output channels from each signal that I've been showing here can only have one consumer. So the let expression lets that signal be used by multiple other signals by making a new multi-channel and feeding in the signal's output channel into that multi-channel, and then it feeds them into yeah, I'm going to gloss over that a little bit. That's how it does the, yeah. Async. So the async function, there's no async node really. It's just returning a new input node. So here, you might remember this kind of syntax from the input node definition before. So it's returning a new input node that will behave like any other input node, but it's going to get events from whatever signal you give the async function. So here it's going to do, so it's going to make a multicast channel. It's going to loop over getting every value it gets from the original signal, and it's going to like new events is like a global. Think of it like it's a global from before. It was on one of the slides that I went over quickly, but basically it sends the ID. So this GUID function generates a new unique ID, and then that unique ID is associated with this async edge. So those word pairs, they end up getting some unique word pair ID, and it gets sent to the new event channel whenever this guy gets a change of message. Okay, we're done. That's Elm. Yay! We're not really done. I'm gonna show some more stuff, but I'll be quick. So I'm gonna gloss over this stuff too. Elm has this whole great system of rendering GUIs. It has this awesome way of you can say here's a video of a bear and here's an image of a tree, and just flow them to the right. You can also say up or down, or even inward or outward, like this. Here's another example. So here's some people and some images of those people, and here's a function where we use this great function infix notation to say, make an image with the file name and put it above the text of their name, and flow right. There you go. And then you can make collages of different things. It's pretty cool. Okay, so so far I've been talking about the thesis version of Elm, but the JavaScript version of Elm is it's really cool. It's there's a lot of things with Elm where it's unclear if how easy it is to build big complex apps with Elm, but with the stuff that it's good for and the stuff that people understand well right now. It's a lot of fun. In JavaScript, there's no parallelism, so we don't have the async function in outside the paper, or at least we don't have the async function in the JavaScript version. So anything asynchronous is like built into the standard library. So there's like HTTP functions and stuff like that. Okay, so now I'm going to talk a little bit about a library that I made. And basically, so I am interested in Clojure. I've been writing Clojure as a hobby for a while. And then I got interested in Elm and thought FRP was really cool, so I wanted to do an FRP library. And so I read this paper, and I thought it was pretty daunting at first, but then I stared at that concurrent ML code for long enough, and it started to make sense. And then I realized that, hey, Clojure has all these channels and stuff. I can build it in Clojure. So here is the library. It is called Zelcova, and a Zelcova is a kind of tree, and it's the only other genus in the elm family. Har, har, har. So yeah, so it's pretty. It's been a lot of fun to make this. So what's that? Oh no. Okay. Thanks. What's that? Good. Command F1. Okay. Okay, so here's Zelcova. Yeah, so this is what it looks like. It's Clojure, so it's a Lisp, so the syntax is different, and it's a dynamic language, so there's no types. So anyway, it's a bit different, but it's you can do a lot of the same stuff with it, and I'll show you some demos. So here's Mario. I got Mario working. Yay. And here is a little drag and drop demo that I made. So you can draw these rectangles, and I just have it displaying the internal state. So yeah, so you can make these rectangles and drag them around, and when you click, they disappear. And it's pretty fun. Yeah, so here's an example of the source. So I just wanted to show this because the drag and drop stuff, I think it would be a real nightmare in pretty much any language, but this is the kind of thing that FRP really excels at, is when you have some complex stream of multiple event sources. And I mean, it doesn't sound so complicated. Everyone knows drag and drop, but there's a lot of things to keep in mind. And once you, it takes a little while to get used to it all and to, understand what it means. But once you get to that point, then it's really expressive and really readable. And there's a lot of functions that I didn't talk about. They're built into Elm and Zelcova, which are other ways of transforming signals. I think I already showed sample on, but there's also keep when ends up saying only when the mouse is down should I care about the mouse position, and then you give it a base value in case it doesn't have one at the beginning. And then Mario was a straight port of the Elm example. So this is I actually wrote out the Clojure code for this demo, or most of it, before I had any working code, as a way of just imagining what it would be like in Clojure. And so you can see the Elm code in comments above. And sometimes it's a little clunkier in Clojure. The ML syntax, once you get used to it, is really nice. But there's a lot about the Lisp syntax that I like too. So, and then, so one of the interesting things about Elm structuring Elm programs is that most of the time you want to do like the vast majority of your code should just be regular functions. Don't worry about signals. And then right at the very end, you just have a little signal graph, right? So it's like you can do all this cool stuff, but regular functions are still like the easiest thing to deal with. Oh yeah, so I was just gonna, so when I first did this, let's see. Yeah, so this is like an early version of it. This is like the first kind of clean working version of it. And it's like a very straight port of the concurrent ML. Here, like, I even named things using the functions from concurrent ML to keep everything in line. And it's like 159 lines of code for that, for all the signal stuff. So this worked. It's tested. Here's some tests. But what I found out was that like it's using a global, it's treating everything as global. So it means that in my tests, I was finding that because the tests are asynchronous, then some tests would run at the same time as other tests. And then I realized that you can't have anything global. So so I changed the implementation so that now in Zelkova, you have your signal graph, which is defined like here's a very simple one. So you have your signal graph that you define here. And then like here I'm using this function, but it's kind of a convenience function that does other stuff. Basically, there's some other function where you somehow get values from the signal graph. And then that function is the only thing that ends up actually wiring up the channels in the background. So when you're just using like keyboard shift and mouse clicks and all these different transformation functions, they are they're just like recipes for signals. They're not, yeah. Command F1. Control F1. Oh. So it was Command F1, but I assumed I had to do the function key. So it's like Command brightness down. Okay. Okay. How's everyone doing for tiredness? Okay. All right, I'll do the epilogue. So I know you're all wondering one very important thing. Is it a monad? Are signals monads? Signals are not monads. Because you can't have signals of signals. It's a very important part of Elm. It gives us some nice guarantees. So it turns out that one of the things that you need in order to be a monad is you need this join function, which is basically like, it would be like having signals of signals and then flattening them into just a signal and then doing something with it. But you can't write that in Elm because of the semantics. Ooh. But it's okay. Turns out that signals are applicative functors, which is nice for a couple of reasons. Here is the definition of what applicative means up top. So don't worry about this too much if you don't know what applicative is. Anyway, it turns out there's a way of implementing, so applicative, think of it like a protocol. and signals can meaningfully implement this protocol. And it turns out that one of the nice things you can do with it is this is what lets, I think at least, unless I have this wildly wrong, I think this is what lets Elm have this nice syntax that lets you avoid like lift 3, lift 4, lift 5, because applicative basically says like you can abstract over all that stuff. Because there's that recursive definition, then you can write things in a certain way. So this is the syntax that Elm has now, which you use these squigglies and squiggly arrows, and then this means like lift those 3 signals into this tuple function. Here's a quote from one of the papers that Evan's paper cites. By fixing the first argument of an arrow type, we obtain an applicative functor. So that basically means that applicative functors can be they're like isomorphic with arrows or something. It basically means that arrowized FRP, which I briefly mentioned before, can be embedded in Elm. So Elm actually has expressive power enough to embed arrowized FRP in it, and there's a library that Elm has called Automaton, which does this. And so this slide is basically saying, so SF is a signal function, arrowized FRP talks about signal functions, and the equivalency that Elm has with arrowized FRP is that a signal of A's is like a signal function from the world to A's. And my understanding is that the way it works in Elm is that you have like a node, a signal node, which has like a little arrowized FRP graph in it that you construct using a different set of functions. And that node can hold state like fold P can, but you use a different set of functions to work with it, and it can be nice for some things. And you can actually define like this embedded system in terms of fold P and vice versa, which is kind of interesting. Okay, that's it. Any final questions? Yeah?
So your is an implementation in Clojure. Does it Elm has an implementation? Is it in JavaScript or Elm is
So the implementation of Elm is the compiler is written in Haskell. I think it's still in Haskell, and but there's like runtime code that's written in JavaScript, and and the JavaScript is not as nice as the concurrent ML.
So with Elm, the simple stuff that you put out, it will kind of generate a relatively nice one-page, like simple HTML with like the necessary runtime. It's a nice standalone thing, but you can, with some flags, if you want to do something like have only one piece of your page be in Elm,
Right.
standard JavaScript, you can have embed it as a component.
Yeah, so when I was talking about how with my library, like you can have multiple signal graphs running, and they just each have their own little world, which is, it kind of sounds like what I was talking about with arrowized FRP, so I'm not entirely clear on the relationship there, but basically with Elm, you can have that happening in different parts of the page, but it's just like each one is like more self-contained, so you can't reach out of that context from within Elm. You need to write JavaScript to deal with the outside world. Yeah.
So if it compiles with JavaScript, when do you run it in code?
Good question. I'm not sure.
Elm is pretty focused on GUIs.
So for the video, the question was if Elm can be used from within Node. Yeah, I kind of doubt it. Someone may have gotten it working, but it actually, like, the way it's sometimes described is actually like it compiles to JavaScript, HTML, and CSS. So it's like, I think it really kind of takes the browser for granted. But someone may have gotten it working in Node. I'm not sure.
Because it's doing the layout stuff too, like
Yeah, actually, well, like one thing I should mention is the way of structuring like elements, building GUIs using the like flow right stuff, that's really nice. But Elm also has a really, whoops, that's not how you spell HTML. Elm has a really nice HTML library, which, as you can see, is pretty fast. And that's what To Do MVC uses to do its HTML. And so it kind of uses the React.js approach of a virtual DOM. It uses a library called virtual DOM, which is a JavaScript library, which is like just that part of React without all the other stuff about React. So it was a good fit for Elm. And yeah, and then there's this like way of writing the nodes in Elm like that. Yeah. So, and in the examples that I use in my library, like these are actually using a similar approach because they're using Ohm right now from Clojure, which wraps React, and it's a really good fit for Elm's FRP model because it's like you just have a signal graph, and then it outputs either some state or maybe even outputs like virtual DOM nodes of some kind. And it's just like, yeah, you just like spit that out to your virtual DOM machine, whatever it might be. It's pretty nice. Yeah. Anyone else? No? Okay. Oh, yeah.
So, just one question I've always had with my little minimum amount of experience with Elm is, so the things you showed there where you have displays of the different HTML things. Presumably, you want to be outputting the output of these signals and things like that. So, are you basically like going and throwing some of the signals and just basically are the display things just themselves just sitting there and going, oh, every time you need, are they signals in themselves where they just go, oh, a new thing came in, so I'm just going to render onto the DOM, whatever currently like work its way through the signal graph? Is that how they're working? Like, you don't have to sit there and go, get me the latest version of whatever's in the signal.
Yeah, I'm not as familiar with the implementation of the rendering stuff in Elm, but I think that it ends up, I think, being like, because it's able to, like Elm, the HTML stuff is just a regular library. There is JavaScript in it. It's not pure Elm that it's written in, but it still works fine with the existing Elm element rendering system. So I think that system is like very efficient on its own.
I guess what I'm asking is, when you're writing Elm programs to display something,
Yeah.
are you basically sitting there going, display, and then giving it a signal, and then it just...
Yeah, oh yeah, right. So that's something I didn't talk about at all, but in Elm, you, I haven't been recording, I think, or unless, anyway. So in Elm, there's this main function, and that's like, so the main signal is, it must be a signal of display elements, and that's what does it. Yeah.
So it's basically the core is a signal, like the signal that you're just composing down.
Yeah. Yeah. So the whole display is like one signal. Yeah. Yeah.
Quick one. Do you know if
Yeah, so Haskell has one called Helm.
I was going to say they can't make a tree of the same things.
Yeah, right. But yeah, I'm not sure about this though, because I remember like Evan was talking about Haskell. The fact that Haskell is lazy is a problem, and it's a problem for like the arrowized FRP libraries in Haskell as well. So, because you can get like space leaks from the laziness basically. So I'm not sure if Helm has solved that problem or not, but I think that it is very much based on Elm. Yeah, it's got the collage stuff here and everything. And then I'm not sure about other languages. Yeah. Good? All right, thanks.